So use your knowledge of exponential properties to rewrite the expression on the right side of the equation so that you can solve for x. So 2 to the third power gives us 2 to the third power. That's easy. Okay. On this one, 2 to what power would give us 2? 2 to what power would give us 2? 1. Good. So x would equal 1. Cool. All right. Now, my question to you is 2 to what power would give me 16? So let's think this through. 2 times 2 times 2 would give us 8. Times 2 would give us 16. How many 2's do we have in total? 4. So x would equal 4. On this next one, we got something weird. We got this little fraction on the right-hand side. What exponent rules do you know that say, hey, take something and flip it and make a fraction? A negative number. So we know that this guy is going to be negative. Let's say that it wasn't negative and this was actually not flipped. 2 to what power would give us 4? Okay, so this would be x equals -2 because this is a fraction. So that made us flip it. And then 2 to the second power would give us 4. Okay, I'm going to give you a second. I know it was a lot of it. Pond in a park. Okay, so on February 12th, a fast-growing species of algae. Okay, so on February 12th, the fast-growing species of algae is accidentally introduced into a pond in an urban park. Okay, so we got February 12th. The area of the pond that the algae will cover doubles each day. If not controlled, the algae will cover the entire surface of the pond, depriving the fish of the pond of oxygen. At the rate it's growing, this will happen on February 24th. Okay, so let's think things through this. How many days are between February 12th to February 24th? 12 days. Okay. All right, so on the first day, we got 1 algae. Okay, so on day 2, we're going to double that. So 1 times 2 is going to give me 2. Okay, on day 3, we're going to multiply by 2. So how much are we going to have? Day 4, how much are we going to have? Day 5, how much are we going to have? Day 6? Day 7? Day 8? Okay. Day 9? Day 10? Day 11? 1024. Day 12? 48. If y'all quit with the, so on day 12, we get 2048, right? I want it where it's halfway covered, right? What's half of 2048?
1,024.
Okay, so on day 11 is when the pond is going to be halfway covered. Have y'all, do y'all have like fish tanks at home? That's me. Okay, my dad's nuts then. Okay, so when you have algae in a fish tank, like one day it's like slightly green, the next day it's like a little bit more green, and then the next day it's like boom, green. Like the whole tank. Can't see nothing. Okay, so that's how algae actually works. And if you ever see it in a pond, the day before, it probably didn't look like that. Okay, this is a side note. So again. Okay, so suppose the area of a pond covered by algae A in square meters is modeled by this function, where W is the number of weeks since the treatment was applied to a pond. Okay, so first of all, we got W is the number of weeks. Okay, that's one thing you need to pay attention to is look at what their, like look at whatever the X value is or whatever the W value is. Because this could have been number of days, this could have been number of weeks, it could have been number of months, etc. How do we use this equation to determine the area covered after 1 day? Okay, my question to you, how many days are there in a week? Okay, thank God. Oh, okay. Okay, so there's 7 days in 1 week. If I'm going to use this equation, what am I going to plug in for W in order to get 1 day?
1 Sunday,
Okay. How'd you get that, Clover?
because it's 1 day out a week.
Right. Okay, so W is the number of weeks, not the number of days, it's the number of weeks. So you would have to get a fraction, 1/7 would be 1 day. Okay, now when we substitute that in, we go into Desmos and we type that in. That's going to give us 181.14 meters square. Shut up. Okay. The point P marks the covered area after 1/7 of a day or 1 day. Okay, so looking at this, we saw in the last one, okay, it was about 188, right? Use either the equation or the graph to find the amount of area covered after 3 days. So after 3 days, it's going to be roughly like 150-ish. But how would we go about solving that for the equation? Okay, so we would do 200 times 1/2 raised to the 3/7. And so that would give us 148 point, we're going to round that to 60 meters squared. Oh, lots of reading. Okay. We're going to talk about my favorite thing in the whole entire world, caffeine. In healthy adults, caffeine has an average half-life of about 6 hours, just so you know. Let's suppose a healthy man consumes a cup of coffee that contains 100 milligrams of caffeine at noon, okay? So each of the following expression describes the amount of caffeine in a man's body. Sorry, the amount of caffeine in a man's body some number of hours after consumption. 4 expressions are included below to represent the different hours of consumption. Determine the number of hours represented in each expression based on the average half-life. Y'all remember back in like chemistry, they talked about half-life? Okay, do y'all remember like what half-life is?
So right that
Yeah, okay, so it's gonna divide into half, right? Okay. Right, and so it's like the number of times that it would take in order for it to completely decay or get to a certain level. Okay, so looking at this, we were told that it has an average half-life of about 6 hours. So every 6 hours is going to drop by half. Okay, so looking at this, they plugged in 1. What does that 1 represent? 1 half-life, which is how long, how many hours? So it's 6 hours. That's what this equation represents. So after 6 hours, that's this equation. What about on the next one? How many hours? Okay, and how'd you get 18? Okay, so that's going to give us 18 hours. Now the next one is a little tricky. It says 1/6. So what is that talking about? 6 divided by what? Okay, so that would be 1 hour. There you go. Okay, so that's gonna be 1 hour. Okay, and then this last one is a little weird. So 100 times 1/2 raised to the t. What is that asking for there? T represents what? Time, or just like we were talking about earlier, the number of half-life. Yeah, so T is going to represent number of half-lives. In healthy adults, the caffeine has an average half-life of about 6 hours. Let's suppose a healthy man consumes a cup of coffee that contains 100 milligrams of caffeine at noon. Write a function G to represent the amount of caffeine left in the body 8 hours after it enters the bloodstream. So this is asking you to write an equation. They tell us that they want us to call it G. So we're gonna say G of, and the other variable that they give us is H. Okay, so G of H. And how much did we start with? 100, which is so sad. That's not enough caffeine for the day. And then,
Well, how much caffeine is that average with?
so like a Celsius has like 200, a C4 has 300 milligrams.
Oh, yeah.
Your sodas only have about 60. Yeah, I do know way too much about food. Way too much. That's okay. All right, now what are we doing? What's the rate? Half. Okay. And it wants us to figure out how many hours after it enters the bloodstream.
Can we just put H for the variable?
We're going to put H for the variable, but we're going to divide it by 6 because I want to figure out how many hours it's going to deal with, right?
Oh, okay. So it would
Yeah.
just be 6 or just 8. H is always after.
Right. Okay. Now over here, we're dealing with a different, similar scenario. The function f represents the amount of caffeine. So we're going to name this guy f. And then we're going to evaluate it at t. Now we're going to write the equation for this. We've got 100 that we're starting with, raised to the multiplied by 1/2, raised to the t. Because t represents 1 6-hour period. So why does g of 6 equal f of 1? So what are they asking us to do with this? Well, eventually we're gonna multiply, but what do we do with this 6?
So we plug it into the 8.
Okay,
Because that's our variable in the function.
okay, so 6 divided by 6, what would that give you? Okay, what about over here? What is it asking us to plug in? Okay, so when I plug in 1 here, that's just giving me 1. Okay, aren't those equal? Because they represent the same thing. 1/2 life equals a 6-hour period. Okay. Okay, so let's talk about this. This is the last thing before we do a little bit of work. Okay, so we got bacteria population. We're talking about bacteria. Okay, bacteria population starts at 1,000, doubles every 10 hours. Okay, so explain why this expression and this expression both represent bacteria population after each hour. Before y'all start freaking out, look at the exponent. What do we know about a power raised to a power? What do we do with that exponent? We multiply. So we do 1/10 times h. When we multiply that, that gives us h over 10. Well, look at what this guy has. Okay, so our power raised to a power rule.
It doesn't even look like a power. It just looks like a slightly smaller number next.
Yeah. Is what we used. I hate giving explanations on here. I was doing a really bad job of that. Anyways, on number 2, it says, by what factor does the bacteria population grow each hour? This is a tricky question because look at what the original says. It says it doubles every 10 hours, right? Okay, so let's think of the equation. What was our initial population? Okay, and we're doubling each hour. And then we've got every 10 hours. So if we wrote this out as an equation, we would say h divided by 10. So how do we figure out the rate for every hour? So that would give me 2 raised to the 1 hour divided by 10. With me? Okay, so it's asking for the factor of it increasing. So we're going to take the rate since it's doubling and raise it to the 1 divided by 10. Okay, so when we plug that into our calculator, I think it's like 1.08 something. I don't remember. I might be making that up. 2 raised to the 1/10. Dang, I'm good. 1.07. Ta-da. Okay, so one of the lovely lessons that we haven't talked about yet is simple interest, compound interest, and exponential interest or continuous interest. So those equations look like this. We got P times 1 plus or minus R raised to the t. We got compound interest that looks like this. And then we've got continuous interest that looks like this. And I'll give you a second to write those down. I know it's been a minute. And simple. Okay. Bye, baby. All right, so P, that's so mean. Okay, so P is going to represent the initial. R is going to be the rate. And T is going to be the number of years. And if you have an N in your equation, N is going to be the number of times it's compounded. And again, this is just kind of like a review from Algebra 1. So on this first one, you got a bank account, okay? Oh, okay. And you start with $100. So that's gonna be your initial amount, right? Okay. It has an annual rate of 4%. And then they tell you that they want to figure out how much money is left in the account after 12 years. Okay, so we're increasing our amount, right? So we're going to use something, this little simple interest formula. So we're going to say $100 times 1. And since we're increasing, we're going to say plus. Do you see how there's this plus and minus? Well, minus would be if like we're taking out money. Okay, but obviously we're not. But 1 plus, and the rate was 4%. Well, we're going to change this guy to a decimal. So we're going to move him over 2 spaces. That's going to be 0.04. And how many years are we putting this in the bank? 12. Okay. So now we're going to type this into Desmos. Yeah, same, man. Same. Okay. And when we do that, we get 160.10. Bro, after 12 years, your $100 only gained like $60. But they also tell you to invest more than $100.
Yeah.
Like they like 10,000.
Interest doesn't really count unless you're like continuously depositing money. That's when you really see the difference.
Yeah. Trust me. Been there, done that.
Of course, the more money you have, the more interest you get. Counterproductive.
Which means you already have.
You have to have money to make money.
Already have. Pretty much.
All right, go ahead and take a look at the next one. We got in 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1985. And how many phone subscribers were in the Centerville at 1994? So how many do we start off with? 285. Okay, are we increasing?
Yes.
Yes, so we're gonna have 1 plus. Okay, so 1 plus, and we're gonna say 0.75 because that's our rate, right? Now, how many years are we gonna put down? Well, we start in 1985, and we go to 1994, so that's gonna be 9 years. Okay, and when we type that into our calculator, we are gonna get 1 plus 0.75. Okay, let's do the 9. There's a lot of people. Okay, 43,870. We're gonna run that too. So we get 43,872 subscribers to cell phones, and that's actually that is what happened actually. Like 2 people had cell phones, and then all of a sudden everybody. That makes sense. All right, so on number 3, a bacteria can multiply at an alarming rate when each. We start with 1 bacteria, and it doubles every hour. Okay, so 1 bacteria, we're doubling every hour. How many bacteria will we have at the end of the day? So what is the exponent that we're going to raise it to?
Are we going to use the continuum?
So this is going to be a times b raised to the x, which is what we've been working with, right? Very similar to what we saw earlier. No, this one's a little weird. Okay, so how many are we gonna have at the end of one day? So we're doubling every hour. So how many hours are there in a day?
24.
How do you stutter on that? Okay. I was like, dang. All right. So that's gonna give us 100. Okay. 16,777,077